So welcome everybody to today's NCCR automation seminar series. Today's speaker is Professor Murat Arcak from UC Berkeley. Murat got his PhD from the same institution as Roy and myself, UC Santa Barbara. Oh no, Roy didn't get it there, but almost. He also received numerous other awards like the NSF Career Award, the Ekman and the Reactive Award, a lot of outstanding milestones in his career. On a personal note, I should say he's one of my personal heroes in the world of network systems and nonlinear possibility-based control. And I'm very happy that he joined for the seminar series. And today he'll talk about hierarchical control for cyber-physical systems and applications to traffic management. Thank you very much, Murat. I'm looking forward to your talk.
Thank you, Florian, for the introduction and the invitation. And congratulations to everybody on this new center on automation. Sounds exciting. I looked through the web page and all the topics seem very exciting to me. So in this talk, I'll be emphasizing hierarchical control. And I understand that's one of the focus areas for the center as well. And I'll be using traffic management as an example throughout the talk. So the motivation is large systems that integrate many components and at the same time that must satisfy complex requirements. That's what I think of as cyber physical systems. So when I say complex requirements, these differ a little from the traditional, set point stabilization or tracking type of objectives that we usually study in control theory. These are things that are perhaps more appropriately expressed, say, in temporal logic or other semantics. So existing design verification methods that we have at our disposal are limited in their scalability to such large systems and also in their ability to address the types of requirements that I talked about. So the talk will be on hierarchical approaches to overcome these limitations. And the running example, as I said, is vehicle traffic management. So this figure at the bottom was for a project that recently ended, actually. It was a CPS project that was studying hierarchical control of traffic networks. So some elements of this project will be visible in this talk. So we study multiple layers of traffic management, starting at the bottom, vehicle level control. And then going upwards, we look at road link level control. That includes things like signal, timing, phase, phase differences between subsequent traffic lights and things of that sort. And at the very top, we have the network level control, which includes routing of vehicles to different routes. So the outline in part one, I'll be speaking about hierarchical control, and I'll be emphasizing the notion of abstractions that enable us to reason about different layers. And we'll see some applications to vehicle level control and reactive signaling at intersections. Those are the bottom two layers of the traffic management system I mentioned. And in the second part, I'll be talking about population games, and in particular, convergence properties to Nash equilibrium. And that connects naturally with the top layer that was routing. As an example, I'll be talking about routing with mixed autonomy. So first part, hierarchical control and abstractions. So hierarchical architectures are standard. Anytime you want to build a large system, that's pretty much, it goes without saying that you need some hierarchy for easier organization. From the internet to anything you can imagine, pretty much. So if you think of a control system and perhaps autonomous driving type of system, at the very top layer, you'll have high-level decision-making capabilities. And below that, you'll have some kind of motion planning or perhaps guidance type of planning or some supervisory control. These can be, in fact, there are different layers. And that layer will be generating set points or trajectories for a feedback control to follow. And the feedback control will be the lower layer and it's the feedback control layer that interfaces with the actual physical system. So the question is, how do we make formal guarantees for the whole stack? And the challenge there is, each layer typically has different semantics. And when you talk about motion planning, you're using a set of tools, perhaps using graphs or whatever, different formulations, different modeling paradigms in each layer. So how do you connect them and be able to reason across these layers? So this problem was nicely articulated by my colleague Pravin Varaya in an older paper. So basically, the problem is connecting the different worlds, and in this paper he talks about the multi-world view of hierarchical systems. So how do we connect the worlds? So this to me reminds me, I'm a Norse myths fan, so this reminds me of what happened? The tree Yggdrasil that connects the 9 worlds in Norse mythology. So we live in Midgard, and gods live in Asgard, and the tree connects them. There's additional connections, Rainbow Bridge, and so on. So in this talk, basically, the role of Yggdrasil in Norse mythology will be the notion of an abstraction to connect the different worlds. So I'll start with the notion of a discrete abstraction. So in a discrete abstraction, you start out with a continuous state model, but perhaps you want to design a supervisory control. And the design of a supervisory control is best done with a finite state model. And so how do you connect these two different models? So how do you start with a continuous state model and represent it as a finite state system? So the natural notion here is that of an abstraction. So, and then once you have the abstraction, once you have your design, then you have to refine this control that you obtain for the top level to be applicable to the continuous state model. So how is the abstraction done? The typical approach is to partition the state space into cells. These could be hyperrectangles, for example, and treat each one as a discrete state variable. Once you have that partition, you do a reachability analysis for each cell to find the successor states under a given control. Okay, and that basically gives you a finite state model. So once you have this finite state model, because it's finite state and because the field of formal methods gives us many tools to design systems, we can tackle complex control requirements such as those that might be expressed in temporal logic. So the formal guarantees that you obtain for the finite state model then carry over to the continuous state model, as long as the abstraction maintains an appropriate simulation relation. There are many of those. In our work, we usually use the alternating simulation relation. Gunther Reissig, which is your neighbor in Munich, he actually has probably the most up-to-date work on this. Some new notions that encompass existing ones on the simulation relations. So here's a stylized illustration of how the discrete abstraction works. A very simplified version. Suppose you have 4 cells, each is a rectangle in this figure. And let's say we start out in the gray cell and we apply one of the quantized values of controls, U1. And let's say the green set is the reachable set. So these are the set of points that you can reach from any initial condition in the gray set under control U1. So because the actual reachable set overlaps with 2 of the cells, in the discrete abstraction, we direct transitions from gray to yellow and purple under U1. And let's say it's not shown here, but let's say under another control U2, we have transitions to red and purple. And that's how we obtain the abstraction in the middle. The synthesis, let's say your goal is to avoid the red state. Perhaps it's an unstable state, corresponds to some kind of collision or something. And then the synthesis is basically eliminating the controls that lead to undesirable behaviors. So some history on this type of approach. The idea of partitioning the state space for hierarchical control started appearing in the 1990s in the control literature. Lunze, Reich, and Young. There's definitely a Central Europe or German Swiss connection here. And then Keynes and Way also did some work on partitioning. And in the past 2 decades, there have been a lot of results in this direction in abstractions and using symbolic control. And this is a partial list of names that come to mind. As always, whenever you think of a list, you leave some people out, and that's always risky. But I want to put the names that I readily associate with this particular niche, discrete abstractions. So there are many computational bottlenecks in this approach. To begin with, we need to do reachability analysis. Then that can be a notoriously computationally complex task. And we actually have to do many of those because we have to do it for each state, right? To determine the successors. So as the number of continuous states grows, the number of discrete states will grow exponentially. And that's one of the major sources of the bottleneck. And that means you'll need to do more and more reachability analysis. And now your abstraction will include an astronomical number of transitions, and the memory requirements will explode and so on. So those are the reasons why in the past, you'd be hard pressed to see an example more than the, thermostat with 1 state or, maybe 2 states, 3 states max. But things have been changing recently. And this is due to many people's contributions, but I'll be telling you about what we have been doing to overcome these restrictions. So on this one slide, I talk about our work on making reachability methods faster and more scalable. And we've been leveraging several control theoretic, system theoretic tools, as well as some learning related tools. And we summarized some of these results in the Springer brief that was published earlier this year. In this book, we cover these methodologies, but we primarily focus on representing reachable sets with hyperrectangles or multidimensional intervals. That's why the book is called Interval Reachability Analysis. The reason is our primary application in mind is symbolic control. And again, here we partition the state space into hyperrectangles. So it's most reasonable to express outer bounds on reachable sets in the form of hyperrectangles. So it's easy to check which other cells you overlap with. However, some of the methods that you'll see here are, also allow broader set representations, but I'm not going to that in this slide. So one set of tools comes from contraction theory. So contraction theory gives us contraction or, in fact, growth bounds around the trajectory. If you start in the neighborhood of an initial condition, how much can the trajectories grow or shrink around the nominal trajectory? So that's the idea in contraction theory. So the way we apply it to reachability analysis is basically by sampling trajectories and being able to reason about the unsampled trajectories using contraction properties around the sample trajectories. And this is illustrated at the bottom left. Another set of tools comes from monotone systems theory. Monotone systems are order-preserving systems. So the picture in the middle illustrates how this is relevant to reachability. So if we have a hyperrectangle, and if we sample the trajectories from 2 extreme corners, the lowest point and highest point, the reachable set will be sandwiched between where those 2 sample trajectories land. That's standard monotonicity, and monotone systems are extremely useful. They have beautiful properties. The only problem is they can be really narrow. I mean, they have restrictive conditions when you want to apply them. But we have introduced variants of monotonicity, which include mixed monotonicity, that completely broaden the applicability of this approach. So And then the third set of tools, part of it made it to the book, and most of it has actually developed after we submitted the material for the book, is based upon statistical learning. So this is a data-driven approach. I know this is the zeitgeist and everybody's talked about this, but it really is useful in this context because very often you may have a dynamical model that really does not satisfy any of the desired properties in the previous methods. Or it could be, it may not even be an analytical model. It could be something like finite elements or some simulation high fidelity model. So what do we do in those cases? So the idea here is to, again, sample trajectories and be able to reason about what's not sampled, but this time not using dynamical systems tools, but instead statistical learning concepts. So basically you're generalizing from samples in the sense of statistical generalization. So at the end of the day, what we can achieve is we give a probabilistic guarantee that our reachable set estimate is covers, say, 1 minus epsilon, epsilon being a small number of the actual reachable set. And we can also give a confidence bound on how reliable that statement is. Along with those, you can actually derive sample complexity bounds, which means that if I give you an accuracy level and the confidence level that I wish to have, then the complexity bound will tell us how many samples we should be taking in order to achieve those bounds. So this is ongoing work. There was some preliminary work presented at L4DC. The year before it was over there in Zurich. I think it was here actually, but I'm not sure if it was in person. Okay, so those are the contributions to make reachability more scalable. And also we can add parallelization on top of this because all of these methods, one way or another, require sampling trajectories, and that can be sampling basically means simulating, right? And then that can be parallelized very often. So we presented some results in CAV 2020 on how far parallelization can take us in terms of scalability. So the results from left to right follow the same order of the results that were in the previous slide, namely first contraction, second monotonicity, and third sampling, basically. That's what I mean by statistical learning. So the black curves represent the amount of time that the reachability analysis took without any parallelization. And you can see the growth with the number of state variables, and you can also see where you max out. Once we reach thousands, even if when the assumptions of the methods I described are satisfied, you'll probably pretty much max out. But you can dramatically increase these bounds by parallelizing. And the 4 other curves that the legend at the bottom shows are done on various AWS platforms. And in one extreme case, we can go up to 1 billion state variables and do reachability analysis in less than an hour. So I should make a caveat here, though. It's not that you can take an arbitrary state model with 1 billion state variables and you can do this in 1 hour. That's not what I'm saying. So we also take advantage of the sparsity in the state model, how states interact with each other. In particular, what led to these results was a freeway model, a traffic flow model, where you basically have a line graph. So that naturally endows the dynamical model with a sparsity level, because the upstream link of the road will affect the density in a given link, and it will be very much localized which links interact with each other. And this method also takes advantage of that sparsity structure. So beyond reachability analysis, so this is about what I showed you is forward reachability analysis. You're basically covering trajectories starting from an initial set. And the problem is when we are using abstraction ideas, we have to do reachability analysis many times because there are so many discrete state variables, so many hyperrectangles that represent discrete states. So what we call sparsity-aware abstraction is actually, again, taking advantage of sparsity in the dynamical model in the state interactions and be able to reduce the number of reachability computations. When we do the interval-based analysis, we can actually decompose the reachability analysis into different dimensions. And if not every state dimension depends on every other state, which is what sparsity is, then the number of calls to reachability routines will be significantly reduced. And we illustrated this at the CDC 2017. And now, so we talked about reachability and having to do reachability fewer times when we have sparsity, but we use sparsity also at a different level in what we call sparse abstractions. So this we do when the dynamical model actually has monotonicity properties in the standard sense, not the mixed monotonicity, it's the standard monotonicity. So what we do in that case is we, instead of recording all possible transitions, we will record the transition from a given state to the largest state in the partial order describing the monotonicity property. And we know that every other transition will be bounded by that extreme state. So that's the idea in sparse abstractions. And for a large class of specifications, control specifications, we can actually make do with such a sparse abstraction and not need the whole set of transitions. In addition to this idea is the idea of lazy control synthesis. In the synthesis, you have to repeatedly do these predecessor set computations. And when you have monotonicity properties, this computation can be significantly simplified. So when we combine those two, this actually leads to a powerful set of tools for synthesis for monotone systems. In addition, sometimes we decompose the larger systems into subsystems and do a compositional synthesis using assumed guarantee contracts. That's a separate line of works. So the monotonicity properties that I've been talking about, they actually arise very naturally in various autonomous driving scenarios. So in this paper by Smith, Saad, myself that recently appeared, we illustrate this in two scenarios. One is a leader following, and the other is an unprotected left turn. You have an oncoming vehicle and you're trying to determine whether you can make it through or not. So monotonicity is useful in both cases, and we can actually leverage those simplifications in synthesis that I described. So this was an illustration with the vehicle level control. I'm now moving one step up to the road link level. So we've shown that these ideas of abstractions can be extremely useful in designing reactive signal control strategies at intersections. So the standard approach to signal control, reactive or not, is to assume pretty much steady state conditions. The most commonly used software for signal timing is called Synchro, and it's based upon such a steady state assumption. But very often we have transient conditions. You may have a sudden surge in demand. You may be at the end of a sporting event or something. So it is more natural in some situations to deal with finite horizon objectives. So our approach is to express the objectives in temporal logic. And this can be things like dissipating queues in a given amount of time, or avoiding saturation in the first place, and things of that sort. And then the finite abstractions that I described allow us to do a synthesis that addresses these temporal logic specifications and satisfies them. Of course, the main issue is how do we get a discrete abstraction for a traffic flow model. So we looked at the self-transmission model that is commonly used for modeling traffic flow. And we used basically discrete abstractions and reachability analysis methods on those models. In fact, this application is where most of those results came out of. So a number of these traffic flow networks actually have intrinsic to them a monotonicity property. Depends on the topology that, monotonicity restricts topology. But what we've shown is that even when monotonicity fails, a variant that I refer to as mixed monotonicity actually does hold in these flow networks. So that means that we can do reachability analysis efficiently and partition the state space. In this case, state space simply means for each link of the road, you have a density as a state variable. Of course, that would be an integer, but you're doing a fluid approximation of that, so you assume it's a continuum. So those are the continuous state variables. And now you partition your state space. It can be a regular grid or an irregular one, as you see at the bottom left. And basically the synthesis tells you what to do, what state to give to the traffic lights when you're in one of these boxes. And the resulting control actually is very meaningful and easy to interpret, because basically by partitioning, what you've done is, each partition here describes a certain set of traffic conditions. The lower bottom says that, both links in this simplified figure have low density. And if you go to one end, you may be in a situation where one link is dense, the other is empty, and basically the state, the signal state is going to be adjusted accordingly. So a summary of this approach, as well as a general tutorial about how to design controllers to satisfy formal requirements, is discussed in this paper, which was published in CSM, Control Systems Magazine, in 2017. So that's the end of part one. No, actually, it's not. I have a couple of more slides. Sorry, it's still early here. So a couple of more slides on continuous abstractions, moving on from discrete abstractions. So the idea here is, instead of a discrete model, we still have a continuous state model. You started with one set of ordinary differential equations, you're abstracting it into another. So why do we do that? The reason is you can get a simpler model as your abstraction, perhaps a linear model that you can then use for model predictive control if you want to, say, do motion planning based on MPC. Okay, and I'll show you another example where we aggregate the states of a large network, and that can also be construed as an abstraction. So basically the idea is to work with a low fidelity model to do your synthesis easier, and to refine this again back to the full model. The full model would be a higher fidelity model in this case. And the refinement basically will take the form of a tracking control here, the goal of which will be to bring the outputs of the two states, two models, closer together. In a sense, this is very similar to what you do in model reference control. You can think of the abstract model up there as the reference model. So how do we guarantee that the two outputs follow each other closely? So it is done by designing a function v, which is like a Lyapunov function that satisfies the dissipation property that you see at the bottom. So this function v is a function of the state x as well as the abstract state x hat. And the second inequality tells us that when v is 0, basically, the outputs match up. Okay, so v is basically a measure of the distinctness of the outputs. And the first inequality is basically a decay condition on v. So this function v is called a simulation function. It was introduced by Antoine Girard and George Papas in 2009, because essentially it's establishing a simulation relation between the two models. So one key here, though, this is, if you insist on decay of v to 0, there are some geometric implications of that. You're basically implying that there is a manifold on which the full state model collapses to the abstract model. Okay, and that gives you very restrictive geometric conditions. Even in the case of linear systems, a number of restrictive conditions have to be satisfied. So what I call the residual term in the dissipation inequality helps us get over those restrictions. So we leave this little term here that depends on u hat and x hat, which are the inputs and states of the abstract model. So you're basically allowing the error, the tracking error, to depend on, to have a residual term that can be modulated by the abstract states, okay? And especially when we allow this residual term to depend on x hat, and that's what we did in this paper at the bottom, we overcome all the geometric restrictions and we can closely follow rather than exactly follow the abstract trajectories. So one example of this is for planning, motion planning, when you separate the motion planner and the low-level control from each other. So the advantage of this approach is the abstraction will be a simpler model that is amenable to online planning, perhaps using model predictive control. And then the heavier computations for finding a simulation function and the tracking control, they would be done offline. So then you can deploy this in real time. So this is illustrated in this figure on a reach avoid specification. You're trying to avoid the gray areas and reach the blue area. But then we are expecting a tracking error because of the residual term that we left there in the inequality. So that means we have to bloat the obstacles to avoid and shrink the target to reach, so that despite the error, we still satisfy the requirements. So as I said, MPC might be a good way to do this with the simplified model. But I want to stress that the abstract model, the continuous abstraction, can also be used as a stepping stone to obtain a discrete abstraction, because as I explained, it's still computationally really complex to obtain discrete abstractions. So if you first come up with a simpler model and then do discrete abstraction, that might simplify the task. So in this paper that I'm citing at the bottom, we actually do that. We use a kinematic model instead of a dynamic model as the continuous abstraction. And then we do a discrete abstraction based on the kinematic model. And that reduction in the number of state variables is very important in making the discrete abstraction possible. So this work was actually motivated by ship docking, which I was told is still a big problem in this industry. Unlike other parts of shipping, the final stage of docking is still done manually because of the high risk of collisions. So basically, the scenario we were studying in that paper is one where you might be experiencing when you're transitioning from the into a docking mode and you're navigating into a harbor area. So okay, so basically this error term that I've been describing is represented with epsilon in this figure. It will depend on, I'm going back now, it will depend on this residual term, right? So if the bigger it is, the bigger the error will be. And this residual term we can control with our planning. When you're designing U hat, which is the control signals you're generating for the abstract model, you can make sure, or you can make it a constraint that this R of U hat and X hat also depends on U hat, right? You can make sure that R is small in order to make sure that the epsilon is small. But doing that limits the permissiveness of the, limits the choices for the planning stage. So in this ACC 2020 paper, we developed an optimization procedure to basically make the planner maximally permissive, meaning that you tune things very carefully using optimization so that you don't create undue conservatism in the planning stage. Okay, so you get the smallest epsilon you can get. And there's also a little back and forth between the planning stages and the control design in this procedure. So this is a final illustration of what continuous abstraction can be used for. This is for network aggregation. So in this case, imagine you have a very large network with many, many state variables corresponding to the many nodes of this large network. But instead, you want to deal with a smaller network size, and you're collapsing your state variables into fewer ones. Basically, that's the notion of aggregation. So this formulation fits nicely into the continuous abstraction framework. And there had been many results in the literature in power systems in the 1980s, for example. People were trying to collapse generators into aggregate, so-called aggregate generators for easier simulation. So basically, the abstraction approach brings a fresh look at this old problem. So in this paper on the left bottom, we illustrated on building temperature regulation problem, where different nodes could actually represent different room temperatures, but we are instead aggregating the rooms into wings of the building and designing controllers for those wings and then refining them to the room. So that's the idea. So that's just an illustration. The paper introduces the theory and then it uses this model to illustrate. I've also been using network aggregation ideas in studying gene expression in multicellular systems. This goes a little far afield for this talk, but the similar aggregation concepts play a key role in trying to predict gene expression patterns in multicellular systems. And the paper I quote at the bottom is, of course, with your Kamash. It's not another one. So the experimental work was done in his lab a couple of years ago. All right, so that is now the end of part one. To transition into part two, which will be shorter, I will play, well, actually it is playing without me playing it, this video of a demonstration that we did 2 years ago. It was just before this COVID closures started. There was already concern about COVID. So we were in Southern California doing these experiments. So these 3 cars that you see boxed are autonomously driven. I mean, we are in those cars, we are steering, but the longitudinal control is completely automated. So the goal here is the following. So we want to keep a short headway between the vehicles. In this experiment, it was only 6 meters. And demonstrate that this can be done safely using vehicle-to-vehicle and vehicle-to-infrastructure communication. Similar demonstrations had been done on freeways more than 2 decades ago. In fact, I know John Ligeros was a graduate student when some of these things were being done on freeways. So the idea here was to do this in urban traffic using V2V and V2I, vehicle to infrastructure communications. The reason we're in this road stretch in Southern California is because 8 consecutive traffic lights had been instrumented for another project to send out signal phase and timing signals to vehicles. And that we actually use for our control. So that's why we use that venue to piggyback on the existing infrastructure. So the idea is to why do we want these platoons? The idea is to use the network capacity, the road capacity more frugally, especially at intersections. There's the so-called slinky effect, right? So when the red turns to green, the first vehicle starts going, and then the second takes its time. It looks almost as if these are connected by springs and it's stretching as we go, right? Whereas here, we really keep 6 meters all along as we accelerate, okay? This can actually be spooky. 6 meters may sound like a lot, but in reality, when you're in one of these cars, it can be really scary, and it's serious tailgating as the speeds increase. I heard screams we were on walkie-talkies, and I heard screams from the other cars a couple of times. So anyway, so with that, I'll move on to the second part. So basically, we've covered the vehicle level and the road link level controls, and I'll be now talking about network level control in the form of routing. And routing brings us to population games. So what are population games? Instead of the traditional game formulations where you have player 1, player 2, and so on, the goal in population games is to deal with a large number of players. And of course, you can no longer keep track of players individually. Instead, you keep track of proportions of the population using each strategy. So that way you get a continuum model, essentially. All right, so one example of this is to congestion games. You can see this on the left. So here you have, in this example, this is just an example, the formulations are much more general. You have one origin destination pair and 3 routes connecting them. So that means you have 3 choices and each one is a strategy. Now, how long it takes will depend on what others are doing. If everybody is taking one strategy, then that will cause congestion and it will take longer. So it's a strategic game. So we assume a constant demand here, and X sub I is the portion of flow using route I. Naturally, their sum will be constant because it's the total demand wishing to flow from the origin to the destination. So the state space in this case is a simplex. So it evolves there. So that's basically one of the most common examples of population games. Population games have a pretty circuitous history. So the book you can see on the right by Beckman and company, some people call it the BMW book. It appeared in 1956. A couple of years after another paper by Wardrop, and you probably have heard of Wardrop equilibrium in routing. Basically, both of these study equilibrium concepts in route choices, but not using any kind of game formulation. Game theory was also being developed at the same time. So it was later that others made the connection between these studies and the work of Nash. And the equilibrium concepts that these book and the other paper introduced were connected to Nash equilibrium in the sense of a population game. Later on in the 1980s, some biologists started looking into evolutionary dynamics and trying to fit Nash equilibrium concepts to that framework. And they introduced some variants of Nash equilibria, such as evolutionarily stable states and so on. And what we call population games today is basically a confluence of all these different threads of research in which the notion of an evolution is interpreted much more broadly. It's no longer really biological evolution, but it's rather the revision strategies of the users. So you may be taking one route one day, and next day you see that your neighbor took another one, they did better, so you switch your route. So that leads to dynamics in the evolution of the proportions of the state variables. And in this part, we address that. So the illustration on the previous slide had one origin destination pair, which meant one single population. So for multiple populations, you have to basically take a simplex for each, and your social state space becomes the Cartesian product of one simplex per population. What defines a population is basically users with the same traits and the same strategy choices. Okay, so, and because the users are eventually anonymous, we just keep track of proportions. So the moment there's a difference in, say, the origin destination pairs, they have to be split into different populations. Even if they're on the same origin destination pair, if they use the capacity differently than others, that means they no longer have the same traits, so they have to be split into different populations. So once you define your social state X, you define also a payoff, which is the most important part of the definition of a game, that depends on the state. So we have N strategies altogether, and F basically spits out a vector depending on the current state that expresses the payoff at that state. So for congestion games, the payoff takes the following form. So basically, it's the negation of the delay, right? Payoff is a good thing, delay is a bad thing. So we basically take the delay, switch the sign, and use it as payoff. So we define a routing matrix, basically that has entries 0 or 1, showing which links in the network serve which routes. Okay, and when you multiply this routing matrix with X, which is the vector of route flows, you translate this vector of route flows to a vector of link flows. So now you have the flows separated into each link, and you apply these delay functions, and those are readily available in the literature for various road geometries and so on. So basically, the delay function is telling you how long it will take to get through a link, road link, if depending on the number of vehicles at that point on that link, right? Naturally, that will be a non-decreasing function, and typically it will be sharply increasing after a certain point when a traffic jam starts. All right, so the output of the middle block then is the delays per link. And to get the delays per route, you have to add up the delays per link on your route. And this is done efficiently by multiplying this vector with R transpose. So that's how we get the structure of the payoff in congestion games. All right, so what is the notion of a Nash equilibrium in population games? First, definition is one of is what's called a best response. Suppose I give you a fixed vector pi that describes the payoffs of each strategy, and let's say that doesn't even depend on the state you're at, right? Then you call a state x bar the best response to pi if x bar maximizes x transpose pi. Okay, it's a very simple optimization problem. Since you're on a simplex, naturally the solution is if pi has one entry that's bigger than all others, the solution x bar will take you to one of the vertices that correspond to the biggest pi, right? So that's the solution. But in reality, of course, the payoff pi is not a fixed constant vector. It is a function of the state. So we call the state x bar a Nash equilibrium if it is a best response to the payoff at that state. So all we've done here is we've replaced pi with f of x bar. So x bar is a Nash equilibrium if x bar transpose f of x bar is bigger than any other x transpose f of x bar. Okay, so that simply means that if you're at that state, no agent benefits from switching their strategy. If you take an infinitesimal portion of the population from one strategy to another, overall they'll be worse off, those that you transferred. So that means nobody has any incentive to deviate from that. So Nash equilibrium naturally describes what occurs with selfish choices. Now, evolutionary dynamics adds on top of the static model revisions. Protocols basically dictate how players change their strategies when they have the opportunity to do so. All right, so basically a protocol describes how agents revise their strategies when they have an opportunity. For example, one that is attributed to Michael Smith, a transportation person. In that case, the probability of switching from strategy I to strategy J is proportional to the payoff that J is offering in excess of the payoff of I. Okay, so simple rules like this dictate protocols. In reality, the dynamical model that this gives you is a Markov process, because protocol really gives you the probabilities of switches, and you have a Poisson process that describes the intervals, the time instance when you get an opportunity to revise your strategy. And when you put them together, it's a Markov process. But what is typically done is people will use approximation results, such as those due to Kurtz, to obtain ordinary differential equation approximation, deterministic approximations that are good on finite time intervals. So this is what an evolutionary dynamic model looks like at the bottom. Rho is the rate at which agents are switching from I to J. So, and this equation shows the derivative of xi, the density in state I. So the second term with the negative sign is showing us at what rate users are leaving strategy I. And that's basically depends on the sum of the rates at which you switch to other strategies. And the first term with the positive sign is telling us at what rate other users from other strategies are switching to I. Okay, so that's the standard structure of the model, and that's for population R. And of course, you have P populations like this, so you put them together in a dynamical fashion in this block diagram, and the way they are coupled is through the payoff vector, which is pi, and that's a function of the state X through the payoff map F. Okay, so you get a feedback loop. And the question is, do the dynamics that result from this feedback loop actually converge to Nash equilibria? We can't take this for granted. In fact, this beautiful book by Bill Sandholm, who passed away last summer, unfortunately, the summer before 2020, shows many examples where the evolutionary dynamics can lead you to something other than a Nash equilibrium. You can have periodic solutions, you can have limit cycles, you can even have chaos in some cases. And his book in chapter 9, I believe, has many examples of that. So convergence, and the side benefit of establishing convergence is, it actually justifies studies, there's so many studies on Nash equilibrium, right? A lot of studies are static. They evaluate Nash equilibrium, how efficient it is, how, what is the price of anarchy, is selfish behavior taking you to a point that is very inefficient. All these studies assume Nash operating at Nash. So basically this type of study, convergence results, justify the Nash assumption. In addition, it addresses one of the criticism of Nash assumptions, which is that how can an agent know everything about the network and go to the Nash equilibrium? Well, the way it's established here is through these protocols that are actually myopic, right? Very often, the way you switch your strategy doesn't require a lot of information. You may be just looking at somebody you select from the population at random. You see if what they are doing is better than yours, and if it is, then you switch to what they are doing. Simple, stupid rules like this can actually lead to protocols and dynamics that take you to Nash equilibrium. So what results exist on convergence? So one set of results uses a monotonicity property of the payoff map, which you see at the top, and a condition on the evolutionary dynamics models that is complementary to that monotonicity. This was shown in a paper by Hofbauer and Sandholm. Later, Jeff Shama, whom some of you know, interpreted this complementary condition as a type of passivity property that we're familiar with in systems theory. So recently with my collaborator Nuno Martins, we generalized this notion of passivity to a notion of delta dissipativity. And what we achieve with this is that we can actually relax the monotonicity condition with what the inequality you see at the bottom. It's basically an incremental quadratic constraint on F. And delta dissipativity is a complementary condition on the evolutionary dynamics model. And monotonicity is simply a special case of that. So here's why this matters. I will illustrate this on a congestion game with mixed autonomy. So again, we have an OD pair, and then this is just an example, by the way, it's far more general than this simple topology. And then we have regular vehicles, human-driven, and autonomous vehicles. The reason why I showed you this video in the intermezzo was because you saw how autonomous vehicles can keep a shorter headway and use capacity much more frugally. So therefore, their contribution to the consumption of resources is not the same as the regular vehicles, but at the same time, they experience the same delay. Whether you're regular or autonomous, you're going through the same roads, you go through the same delay. So there's a natural asymmetry in how you use a resource and what you get as a payoff. So this model by my colleague Roberto Horowitz and his former student Negar Meir is a simple model that shows this asymmetry, that accounts for this asymmetry. So what you do is you look at the autonomous flow, you basically multiply it with a discount factor mu that is smaller than 1 and add it to the regular flow. And that gives you an effective flow, and you apply delay functions to that. And then the delays that you get is the same whether you're autonomous or regular, okay? This model is great, but when you look at it, the monotonicity property that existed for the previous model without mu is now lost. So the results I mentioned can't be applied. However, you can prove a generalized quadratic constraint, which is as follows. So the matrix M in the middle takes this form with a weighting matrix, and the weighting matrix accounts for the discount factor mu. Okay. So what we did in this example is we showed that we can actually prove delta dissipativity of the evolutionary dynamics models with this M, and therefore we can reach the same types of convergence guarantees. All right, so I don't want to go over time. So some conclusions. We've shown that hierarchical architectures are critical to cyber-physical systems, and they allow us to make formal guarantees for the whole stack rather than for individual layers in isolation. And there are many research opportunities for reasoning across layers and for connecting the controllers for individual layers, and your center is pretty much doing that, among other things. So some of ongoing work. So we have started looking into, in a new project, into traffic management under extreme demand conditions. And the application of that is to evacuation scenarios, which is unfortunately something we've come to live with. I mean, not in this area so far, but in other parts of California because of the fires this time of the year. The picture you see at the left is from a recent evacuation last month of Salt Lake Tahoe, where people spent a good part of the day on the road stuck. I've been told that in California, there are 100 zip codes where the exit road capacity per resident is less than the town of Paradise, where 85 people died 3 years ago in a fire, and some of them were trapped in their cars. So evacuation is serious business, and it needs to be done efficiently. So we're working with this company called Zonehaven, and Zonehaven is providing basically a collaboration platform to first responders and to residents with apps facing each side. And they have household data, and they have split the areas into different zones. So basically our goal is to provide decision support to first responders. And what are some of the control knobs? What are things you can change? There are things you can do. For example, first and foremost, you can choose the timing and sequence of evacuations by zone. Okay, that's one of the most important control knobs. If you know what's going to happen in traffic, you can avoid jams that way. You can also divert some of the traffic to refuge areas, large parking lots. Anytime you have a large concrete structure not surrounded by fuel, I mean, not including fuel inside, you can basically make a temporary refuge in an area like this. And also you can switch the directions of the roads. Lanes can be reallocated. You see in this picture in the bottom that, the outgoing lane is full, but the incoming lane is empty. So some of that can be reallocated. So this is ongoing work, so I will not go into much detail. Hopefully at a future time, I can tell you more about the results. So here's a limited list of papers for further reading. Not everything that I mentioned in the talk, but some things that are, I guess I picked them by being more recent and perhaps being a little, more descriptive of what's happening. So on that note, I will thank the National Science Foundation and Air Force for their support and all of the collaborators I mentioned along the way. Thank you again for the invitation, and I'm happy to take any questions.
Okay, thank you very much, Murat, for the